The engine is where rockets get brutally honest. Heat finds every weak spot. Vibration shakes every loose part. Leaks turn into fire fast. For 50 years, the standard solution was protection. Engineers wrapped engines in heat shields. They added fire suppression systems to put out flames. They added heavy brackets to hold plumbing in place. It worked, but it created a heavy, complex machine that was hard to fix. SpaceX looked at their new Raptor 3 engine and made a different choice. They stripped off the protection most engines hide behind. External heat shields came off. Secondary support parts came off. Fire suppression hardware came off. It sounds reckless at first. It sounds like a team cutting corners. But they did not remove protection and hope for the best. They moved the protection inside the engine itself. You already know this feeling from other machines. You see a device covered in guards and warning labels and you think, this thing must be fragile. Then you see a machine that runs bare, with thick metal and clean lines. You think they trust it. Raptor 3 is that second kind of machine. People called it a naked engine because the outer layers are gone. But the core claim is simple. SpaceX removed the extra structures around the plumbing. Then they built the cooling directly into the engine body. That is the breakthrough. It is not a paint job. It is a new layout. Here's the thing. Rocket engines are basically controlled fires. They burn fuel at insane rates. They do it under huge pressure. If you add extra shields outside, you add weight. If you add extra braces outside, you add weight. Weight is the enemy. Weight steals cargo. Weight steals safety margin. So the dream is always the same. Make it lighter. Make it simpler. Make it strong enough anyway. SpaceX put numbers on the table that show why this matters. Raptor 3 weighs about 1,120 kilograms fully installed. That is down 1,100 kilograms from Raptor 2. That is not a small trim, that is a major cut. It means the engine is doing more work with less mass. That is competence you can measure. Now lock onto the stack count. One Starship flight uses 39 engines total. That is 33 on the Super Heavy booster and 6 on the ship. So a savings of over 2,400 pounds per engine matters. Multiply it by 39 engines. The total savings hits about 94,575 pounds per flight. That is weight the system no longer has to lift. That is more room for cargo. That is more room for fuel. Think about that for a second. One engine gets lighter, then every engine gets lighter. Then the whole vehicle gets a free gift. It is like shaving weight off every wheel on a truck. The truck drives better, it brakes better, it hauls more. You did not change the road, you changed the machine, but weight is only half the story. The real story is heat. SpaceX's stated rationale leans on regenerative cooling. That is a technical phrase, so let's keep it simple. It means the engine uses its own fuel to cool itself. The fuel is very cold methane. The fuel flows through built-in channels in the engine body. Those channels soak up heat. Then the fuel goes on to burn. So the same fuel does two jobs. It cools the metal, then it powers the engine. That is the kind of trick that feels like turning the impossible into the possible. And this is where the design choice clicks. If the cooling runs inside the metal, you need less outside shielding. If the plumbing lives inside the body, it is less exposed. If fewer parts sit outside, there are fewer things to snag. There are fewer things to break. There are fewer things to inspect between flights. That last part is the quiet win. You cannot fly fast if you spend forever checking small parts. SpaceX removed external heat shields from Raptor 3. Heat shields are like armor plates. They protect what sits under them, but armor adds mass and hides what is happening underneath. That can slow inspections. If you want rapid reuse, you want to see the engine. You want to access the engine. Taking shields off helps that, if the engine can survive without them. The second big change is the removal of secondary structures around plumbing. Plumbing on a rocket means the tubes and lines. They move fuel and fluids. Those lines can shake, rub, or leak if stressed. Raptor 3's change is to internalize plumbing into the engine body. That means fewer exposed lines. Fewer exposed lines means fewer clamp points. It also means fewer spots where heat can cook a line. The third change is the removal of dedicated fire suppression hardware. That sounds wild, but the point is not no safety. The point is less chance of fire. If you reduce leaks, you reduce fire risk. If you reduce exposed plumbing, you reduce fire risk. So they are trying to solve the cause, not just fight the symptom. Now stack in the power numbers. Raptor 3 is claimed to push thrust to 280 plus metric tons force. More push with less mass is the dream. It means the engine is doing more work per kilogram, and when you have 33 engines under Super Heavy, every extra bit of push matters. Super Heavy and Starship are not small rockets. They are a full system meant to fly often. Fly often is where most rockets fail as a business. They can fly once or twice, then they hit repair walls. SpaceX wants fast turnaround. Engine complexity is usually the killer of that plan. Engines face two brutal constraints. They must survive firing, and they must survive the rough world around them. The area under a booster is violent. Hot exhaust hits nearby parts. Vibrations shake everything. Small leaks can happen. When a small leak happens near heat, it can become fire fast. Older designs patch the risks with extra hardware, but extra hardware is a trap. It makes the engine heavier and harder to fix. The more parts a machine has, the more time it demands. Now we hit a near-miss moment. Imagine an engine test. The countdown hits the last minute. The lines fill. One sensor reads hot. You are 30 seconds from full burn. With lots of external shields, you might not see the problem early. With a naked engine, you can spot odd heat marks sooner. That can save a test. That can save a vehicle. That is not drama. That is practical. Cutting hardware demands precision. Internal channels are harder to build than simple outer shields. Internal plumbing means tight routing inside metal. That increases manufacturing demands. If you mess up a channel, you scrap the part, so the team must be extremely confident in quality control. This is where the technical mastery trigger sits. You don't get to a naked engine by optimism. You get there by nailing the basics. Metal forming, welding, machining, inspection. You need a process that can hit the same result every time. Now connect this to the factory floor. The prompt mentions a massive build time reduction. Raptor 1 engines took over 11 days to build. Raptor 3 engines are targeting about 24 hours. That is not a small improvement. That is a factory reset. It tells you the early design was too complex to scale. So SpaceX made scaling the top goal. They cut parts, they cut joints, they made the engine friendlier to the line. The part count dropped by 30% or more. That is a brutal cut. If you want speed, you reduce parts. Fewer parts means fewer joints. Fewer joints means fewer leak paths. Fewer leak paths means fewer tests. Fewer tests means less time. It is a chain. Cut the first link and the whole chain shrinks. Now define a keyword. A joint is where two parts meet. It can be a weld or a bolt. Joints are weak spots because joints add surfaces that can leak. The best joint is the one you delete. The new design deletes brazed joints and bolts. It uses welded, unified structures. Welds can still fail, but fewer seams can reduce risk, and fewer bolts can reduce build time. Think about that for a second. Every bolt needs a hole. Every hole needs drilling. Every drilled hole needs a check. Delete the bolt and you delete the whole stack behind it. That is resource efficiency in plain form. Now let's validate victory with competitive metrics. The cost drop is significant. Raptor 1 cost about $1 million. Raptor 2 dropped to about $500,000. Raptor 3 is targeting $250,000 or less. That is a 4-time cost reduction. If you have to build hundreds of engines, that is huge. It can free money for testing and pads. It is like fixing a leak in your house budget. The prompt says they are targeting an output of 1 engine per day. A daily engine output sets a new bar. It also changes what Starship can attempt. With a slow engine line, you fly rarely. With a fast line, you can accept losses and test more. That is competitive reality. And this is where the Mars cargo story comes in. Remember that 94,000 pounds of weight saved? That is dead weight removed from the ship. When you remove dead weight, you can add payload. The prompt estimates this adds 10 to 20 tons of useful cargo to Mars. That is not small. It is the difference between arriving with bare essentials and arriving with spares. It also changes the tanker equation. To get to Mars, Starship needs to refuel in orbit. That means tanker flights. The prompt suggests the weight cut could save 2 tanker flights per Mars mission. It drops from 1620 down to 14 to 18. If you plan to send 1,000 ships, that is 2,000 fewer tanker flights. That is a massive reduction in work and risk. That is how timelines move by years, not by speeches, by removing steps. Now we shift to the booster because the engine is only half the system. The super heavy booster had its own weight problem. It uses grid fins to steer as it falls back to Earth. These fins are huge. They weigh about 3 tons each. Early boosters used 4 fins. 4 corners felt safe. But SpaceX noticed something. The 4th fin was not doing much. During the fall, the booster comes in at a steep angle. The 4th fin often sat in dead air. So they removed it. They went from 4 fins to 3. That sounds wrong, you feel like you're losing control. But they made the remaining 3 fins bigger and stronger. They moved them to a better spot. They spaced them unevenly to match the airflow. The result is a lighter booster that steers just as well. Removing 1 fin saves about 3 tons. That is another truckload of dead weight gone. And here is the magician move. They did not just remove a fin, they changed how they catch the booster. SpaceX plans to catch the booster with tower arms. To do that, the booster needs catch points. They built the catch points into the grid fins. That allowed them to remove the landing legs entirely. Landing legs are heavy and complex. By removing legs, they saved even more weight. They also removed a failure mode. You cannot have a leg failure if you do not have legs. Now connect the engine to the catch. Catching a heavy booster is hard. It hits the tower with a lot of force. Catching a lighter booster is easier. Raptor 3 makes the booster lighter. That means less force on the tower arms. It means less shake. It also means you need fewer engines firing to slow it down. With a heavy booster, you might need 13 engines to land. With a lighter booster, you might need only 3. 3 engines are easier to balance than 13. That reduces the risk of a thrust mismatch. That reduces the risk of a crash in the final seconds. So the engine upgrade actually makes the landing safer. It makes the catch tower last longer. It makes the whole system more robust. This is system thinking. One change at the bottom helps everything at the top. Now we need to talk about the skepticism. You have seen too many big promises fade. You have seen numbers that look great on paper but never happen. You are right to be careful. But the evidence here is in the hardware. We have seen the Raptor 3. We have seen the 3-fin booster design. We have seen the test catches. The numbers fit the physical changes. A smaller, simpler engine should be cheaper. A lighter booster should be easier to catch. This is not magic, it is engineering, and it points to a clear future. If SpaceX can hit these targets, the cost of launch drops hard. Falcon scale economics for a giant ship becomes real. That opens the door for heavy cargo. It opens the door for big space stations. It opens the door for Mars supply chains. The engine is the key. If the engine is expensive and heavy, the door stays closed. If the engine is cheap and light, the door opens. Raptor 3 is the attempt to kick that door down. It raises engine power by over 50% compared to the first version. It cuts mass by over 30%. It cuts cost by nearly 75%. Those are the kinds of jumps that change industries. It is not just about going to space. It is about staying there. It is about building a railroad, not just launching a bottle rocket. The railroad needs engines that work. It needs engines that are easy to fix. It needs engines that don't cost a fortune. Raptor 3 is trying to be that engine. And if it works, the rest of the system gets a green light. The factory speeds up. The flight rate climbs. The mission grows. That is the path from impossible to possible. It starts with a single naked engine on a test stand. And it ends with a fleet that can actually move humanity. Competitors are watching this closely. They know what these numbers mean. They know that a production line building one engine a day is a weapon. They know that a booster without legs is a statement of control. The gap is not just in technology, the gap is in the factory. The gap is in the mindset. While others polish designs, SpaceX strips them down. That is the difference. And that is why the scorecard looks the way it does. The next few years will test these claims. The test stand will be the judge. Gravity will be the judge. Mars will be the judge. But right now, the engineering logic is sound. Simpler is stronger, lighter is faster, cheaper is sustainable. That is the bet. And looking at the hardware, it looks like a winning hand.